So we are looking at graphs today. We'll see the terminology first, then graph as abstract data types, then the applications of graph. First is the definition. Graph is nothing but the set of points that are joined by lines, and graphs also represent the relationship among the data items also. And G is equal to V comma E. This is an ordered pair. That is a vertex or edges. A graph consists of a set of vertices and edges. This is a graph. A subgraph is what? It consists of a subset of graphs, vertices, and a subset of its edges. So if this graph we call it as A, this one is A1, this is A2. So A1 and A2 they are subgraphs of this graph A, means whole graph. Then this is a simple ordinary line graph. This is a line graph. We have these as called as vertices. These are edges. This is a simple graph showing a campus map. You have dormitory, library, gymnasium, student union. All these are connected. And if you want to find the subgraph, this is the subgraph taking this as one part. So this is the subgraph. Now a graph that is connected. See all the vertices, they are connected. There is not a single node or the vertex which is left. In this case, we have two vertices which are left. So this type of graph, they are known as disconnected graphs. And a complete graph means all the vertex or all the vertices, they are connected to the other vertices. Like this one is connected to these four. This one is connected to, means every node is connected to other node. This is called the complete graph. This is an example of a multigraph, which is not a graph. This is not a graph. And this is about the self edge, which is not allowed in a graph. We'll see about this case. A simple path means it passes through vertex only once. This is a simple path. What about cycle? A cycle that begins and ends at the same vertex. This is a cycle. And a simple path is, again, this is also a simple path, but it should pass through vertex only once. So this will not be a path, simple path. This will be a path. This will be a path because it should not pass through the vertex again. That is a simple path. Cycle means the begin and end at the same vertex. Simple cycle, a cycle that does not pass through other vertices more than once. Okay, it can pass here, but other vertices not twice. Connected graph, each pair of distinct vertices has a path between them. Each pair of distinct vertices should have a path between them. A complete graph, as we have just seen, each pair of vertices or distinct vertices have an edge between them. And a graph cannot have duplicate edges between vertices. No duplicate edges is allowed between vertices. A multigraph, this does not allow multiple edges. When labels represent numeric values, that is some weight is there, we call these graphs as weighted graphs. Undirected graphs, if edges do not indicate a direction like this, the edges are just like this, no direction, we call them as undirected graphs. What about a directed graph? This is a directed graph or a digraph. Each edge has a direction. Now, let us take the example of weighted graph and directed graph. These vertex 1, 2, 3, 4, all vertex, if they are connected, any of the two vertex have certain path or certain weight along with their path. This is the weight we call, and every edge has certain weight. We call this type of graph as weighted graph. And a directed graph means all the edges must have an arrow. That is, they should point that I am moving from San Francisco to New York and coming back. Right? What about graphs as abstract data type? ADT graph operations include first to test whether the graph is empty or not, then get the number of vertices in a graph, get the number of edges, number of vertices, number of edges, test whether it is empty or not, see whether edge exists between two given vertices, whether edge exists or not, Insert vertex in graph whose vertices have distinct values that differ from the new vertex value. So inserting a vertex in a graph is also the operations which comes under the abstract data type graph operations. Then we have inserting an edge between two given vertices in a graph, inserting an edge, removing a specified vertex, say removing this one from a graph and any edges between the vertices and the other vertices, removing the edge between two vertices in a graph, and retrieving from graph vertex that contains certain value, retrieving the value. So we'll see the directed and connected one. How to implement the graphs? To implement graph, we have two options. We can either make a adjacency matrix, or we can also use the adjacency list. So this is your graph, a directed graph, and the corresponding adjacency matrix is shown here. All the vertex, how many they are there? 1, 2, 3, 4, 5, 6, 7, 8, 9. So you have 9 vertices which are written here. Again, the 9 vertices are written here. The same vertex. And we have to see that, or we have to put one whenever we have a path between them or an edge between them. Not path but edge. P and R, are they connected? Let us see. P and R, yes, they are connected. So all these ones, say, take one more example. T and W, because it is 1, that means they must be connected. Or they must have an edge between them. W and T, yes, W and T has this one. So we are going to fill 1 only when you have an edge between these two nodes. Otherwise, we'll place 0. So it is going to take a lot of space, but representation and operations are good here. This was an example of what? See, this was an example of directed graph. So directed graph shows 1 only when W is connected to Y. So W and Y, see, W and Y. This is W and Y. And what about Y and W? Y and W is 0. Y and W has no value. Why? Because in directed graph, W has a direction to Y. Yes, we have a directed edge from W to Y, but we have no directed edge from Y to W. That is why we have placed a 0 here. But in the case of an undirected graph, see, this is an undirected graph. Again, we are going to take the edges, vertices A, B, C, D, A, B, C, D, A, B, C, D, and from A to path A, the self edge will be infinite. See, all the values in this diagonal of this matrix, it correspond to infinite. But B and A and B both have the value 8. Why? Because B and A, they share an edge with a weight 8, and similarly for others. So we will have the values corresponding to CB and BC also. They both will be 9, like this. And then the other way of implementing graph is the adjacency list. So for a directed graph, how to implement the adjacency list, or how to represent this graph with an adjacency list? So in this case, we are going to take all the edges and we'll make these pointers, say P, Q to Z. These are around similar. This graph is similar to what we have seen just now. So we have 9 vertex here. All these vertex are shown here. Now we'll start with P, and this is a directed graph. Please mind it that the arrow is there, so there is a direction. And this P, start with P. P has a direction or direction to R. So we'll place a list. So this is a representation of a linked list. So we have a link from P to R. Then since P is also connected or directed to W, then we again have a link to W. And because there are no more directions from P, we do not have any other. So this is null. This is null. Let us take one more, say W. Now W is directed to Y and is directed to S. So first in W we will write S, and then after this S, this is a pointer. W has a pointer to S, and this S will have a pointer to Y, and then null. Let us take 6. What about 6? This means X. X has no edge or no direction to any of the other vertex. So we will not place anything, we will place null here. This is how we represent the graph or the directed graph using the adjacency list. This is a weighted, you have a weight, undirected, no direction graph, and how to write the adjacency list of this. And the same procedure will be there. We'll write 0 to 3, all these number node are there, but we are interested in A, B, C, D. We have pointers, these are the pointers, and this is pointing to what? A is pointing to B, but the weight is 8. So we'll have a list with content B, then the weight, and then we have one more thing here. What is this? A is connected to B, or A is connected to D also. So A will be with B, and there will be one more list or one more pointer to D, and it says that the value is 6. Now A is done, so we'll place a null. We'll take one more example, say D. What about D? D is connected to A, so we have to write A here, and then 6. 6 is the weight, and then null. This is how we implement a graph using the adjacency list. This is a weighted undirected graph. Then we come to the graph traversal. In graph, you can traverse means visit all the vertices that it can reach, and it will happen if and only if the graph is connected. If the graph is not connected, you will not be able to traverse through the node or the vertex which is not even connected. So connected component is subset of vertices visited during the traversal that begins at a given vertex. We have two type of graph traversal: depth first search and breadth first search. So in depth first search, it goes as far as possible from vertex before backing up. So it will just go deep down. It will go as far as possible from a vertex before coming back or backing up. This is a recursive algorithm. For example, to traverse a graph beginning at say vertex V, and by using say a depth first search, the recursive version would be something like this. This is a DFS of vertex V. First we mark V as visited, and for each unvisited vertex U which is adjacent to V, so U is adjacent to V, first we'll go here. Then again say some P is there, we'll go here. And we again call this DFS U, that is again this one. We have to see that if U is connected to any other P, then again P is connected to M. So all this will be traversed, then we'll come back and then we'll go to some other node. This is an iterative algorithm, and we use a stack here. In depth, the depth first search uses a stack, and we'll see what breadth first search uses. Maybe breadth first search may use say Q, but for the first case, depth first search uses a stack. So this is a traversal of a graph you have just seen, beginning at vertex V by using depth first search, iterative version. We start with DFS, we have just seen. Then how to use a stack? We start a stack with a new empty stack. Then we push V onto stack and mark it as visited. S.push, and then we mark V as visited. And then there is a path from V at the bottom of the stack S to the vertex at the top of S, while S is empty. We do it till the stack is empty. And then if no unvisited, let me show you first. How did it happen? While we are taking while, and then we have a loop. While this stack is not empty because we have already pushed, we are pushing the values which are being traversed. So while that is not empty, we pop. So if we find no unvisited vertices which are adjacent to the vertex on the top of the stack, then we pop. So if say P was there, and then what we are going to do, we'll pop P, U, V like this, if there is no other to be placed. And we do it till it is empty. And otherwise, if it is not the case, we select an unvisited vertex U adjacent to the vertex on the top of the stack, and we push it onto that U onto the stack and mark U as visited. So this is depth first search. The visitation order or the traversal order for depth first search would be something like this. See, first we will travel here 1, then 2, and we can't backtrack. We have to do it depth wise. Then we have to go to Q. Then we cannot again backtrack. The adjacency of Q is R. Now there is no other connected, so we'll come back to Q. Then we find if some other way or some other is connected. Then we say okay, 5 is connected. Okay, now this is done. There is no node here. We come back and we move back. See, U is already visited, so we'll see all the adjacent node. T is not visited, so we'll visit here. Then we backtrack, then we go back to V, and we see, okay, we have taken 2 now. For this node, we need 7. So we go to 7. We come in. There is no node to be traversed. We come back, and then we see, okay, 2 and 7 has been traversed. What about 8? Because this has not been traversed. So 8. So the whole idea is the traversal would be like this. First, let me write it here. V, U, and I suppose this was Q, R, then S, T, then W, and X. I hope I've repeated X. No, it is okay. Then about the breadth first search, as I said, first the basic idea you just have to learn that we will take all the values in the order of their levels. So we'll start with V. We'll cover all the values in this level. U, W, and X are at same level. So it will come as first we'll traverse U, then W, then X. Okay, this is done. We'll come to the another level. Now in this level, Q and T are at the same level. So we'll visit Q first and then T. Then we come to this level. Now R and S. These are at same level. So R and S. I hope you got the idea of traversing. And this is a connected graph, and we have cycles also here. So how to depth first search in this particular graph using stack. I hope you'll be able to know. First, we start with A. And then whichever you want to proceed, you will place it to this stack. So A will be placed to the stack, and then next one will be, say, B, then A, B, C, D, A, B, C, D, G, A, B, C, D, G, E. Then we are going to pop E. A, B, C, D, G, A, B, C, D, G, F. Then we'll pop F, and then A, B, C, D, G. Then we'll pop G, then D, then C, then B, then A. Likewise. Okay. And this is how we backtrack until we reach the A, and we find the stack as empty. So the result of that first traversal we have just seen of the graph with vertex A. I hope you are able to understand this. What about the breadth first search? We have just seen breadth first search. It visits all the vertices adjacent to vertex before going forward. We have just seen it. So in that figure. So breadth first search uses Q, and the depth first search uses stack. This is how it is done. We traverse a graph beginning with, say, vertex V by using a breadth first search. So we enable a Q, that is an empty Q, and then we visit V and mark it has been enqueued. And while Q is not empty, we again dequeue it, and for each unvisited vertex U which is adjacent to W, we mark U as visited, and then we again enqueue it, and this goes on. So this is the result of the breadth first search beginning at vertex A of the graph we have just seen. So you just have to understand, don't worry about this. We just have to understand that the levels we have to traverse according to the level, and the queue will be filled and unfilled according to the nodes at the same level being traversed. Now coming to applications of graph, we have various applications of graph. So this is one of the example of application, that is how we can place. This is a graph of previous figure arranged according to the topological order, and we'll be taking this application of graphs in the next discussion. Thank you so much, and we'll be taking the applications like MST and all traveling salesmen in the next session. Thank you so much.